Hello everyone. In this video, we will discuss section 3.3 of our textbook, which is all about vertex form for a quadratic function and completing the square. First off, let's look at the graph of the quadratic function f of x equals 2x squared minus 4x minus 6 that we see drawn right here. Now, we saw this graph already back in section 3.1, the very first thing we did, if you want to look back at that. I claim that this function can be represented alternatively in the form 2 times in parentheses x minus 1 quantity squared and then minus the 8 on the end. To show that this is true, recall that x minus 1 squared means that you're taking x minus 1 and multiplying it by itself. And if I want to multiply x minus 1 times x minus 1, I can distribute or FOIL. I can do x times each term in the second set of parentheses, which will give me x times x or x squared, and x times negative 1 or negative 1x, which can be written as just negative x. And then I can take the second term in the first set of parentheses and multiply it by both terms in the second set of parentheses. Negative 1 times x will give me negative 1x again, and then negative 1 times negative 1 becomes positive 1. All of this product is being multiplied by the 2 out front, so I've written it all in parentheses, and then we are still subtracting the 8 off the end. If you like, you can combine your two like terms in the middle before you distribute the 2. Negative 1x minus 1x will give me negative 2x, and then we'll still have the plus 1 in the parentheses before the minus 8 outside the parentheses. This 2 gets multiplied by every term inside this set of parentheses by the distributive law. 2 times x squared is 2x squared. 2 times minus 2x is minus 4x. And 2 times the 1 on the end is positive 2. We still need to subtract 8 from all of this. The only surviving like terms are our constants, plus 2 minus 8. When we do the arithmetic, we get minus 6. And note that this 2x squared minus 4x minus 6 is exactly what we claimed it was. What we started with, you may recall, is referred to as the standard form of a quadratic function, which is written as ax squared plus bx plus c. The form I just multiplied out, the 2 times x minus 1 squared in parentheses minus 8, this is an alternate way to represent a quadratic function, and it is called vertex form. Why is it called vertex form? Let's refer to this graph. Notice that the vertex, or the turning point, of this quadratic function occurs at 1, negative 8. If you look closely at what I've called vertex form, notice you can see that 1 hanging out inside the set of parentheses, as well as the y value of the vertex minus 8 hanging out on the end. This relationship doesn't just happen here, it's something that happens in general, and we will define vertex form for any quadratic. We say that a quadratic function with variable x is expressed in vertex form if we write it as y or f of x equals a, which is the leading coefficient, i.e., the number in front of the x squared when you're in standard form, times x minus h, whole thing in parentheses squared, plus k, where h is the x coordinate of your vertex and k is the y coordinate of your vertex. So off to the side here for a second, if we go to the example we just talked about, what we're going to have is going to be the following. So it looks like this. And vertex form is a times x minus h squared plus k. We can see then that playing the role of a is 2. So a is 2 from this. We can also see that playing the role of h, the number after the minus sign in the parentheses, is 1. So this tells me that h is 1 in this case. And then finally, playing the role of k is going to be whatever number we have after our parentheses and squaring. So the number we add on, you would add on -8, which is the same as subtracting 8. This is going to be playing the role of our k. And it's no coincidence here that if we group hk together, that gives us our vertex -1, 1, -8, which matches what we see on the graph. Okay, so that's the claim here. HK, when you're written in vertex form, is the vertex of your graph. And this is just a statement that makes it clear that f of h equals k means that h, the x value of your vertex, when you plug it into your function, will result in the y value of the vertex, which is k. It's always true that the number a out front matches the leading coefficient or the constant a that we see in standard form. Here, our standard form, we see that a is 2, and note that it is also 2 in our vertex form. This means that if a is positive, then we have an upward-facing parabola, making it so, let me draw it, an upward-facing parabola if a is positive, making it so that your vertex is located at the bottom of the quadratic, and hence making k the lowest y value of the function, since k is the y value of the vertex. So that's as low as you can go on an upward-facing parabola. If a is negative, you open down instead, forcing your vertex to be on the top, and hence the y value of your vertex will be the highest y value that your quadratic function ever hits. Our first example asks us to give the coordinates of the vertex of the graph of the quadratic function w of z equals 3z plus 4 quantities squared minus 7. And in our case, our vertex form has been given, but I'm just going to rewrite the formula with a z instead of an x. So our formula is a times x minus h squared plus k. I'm going to write it as a times z minus h squared plus k. And the goal is to figure out what would be playing the role of h and k in 3 times z plus 4 squared minus 7. We're going to approach this in the following way. I'm just going to rewrite this guy over here so I have plenty of space. There's the minus 7. And right now, notice that the minus sign is built into your vertex form formula, and I do not have a minus sign inside the set of parentheses over here. If I'm going to correctly identify h, I'm going to have to somehow insert a minus sign. Addition is the same as subtracting a negative, so I can rewrite adding 4 as subtracting -4. Minus minus 4 is the same as plus 4. Similarly, subtracting off 7 on the end would be the same thing as adding -7, because when you add a negative, you're really subtracting. This helps me out because I can now see the number I'm subtracting from z happens to be -4, and that's what's playing the role of h, whereas the number that I am adding on the end is -7, and that ends up being my k. Hence, the vertex of this quadratic function is given by h comma k, where h is -4 and k is -7. Okay, one way to think about this is h is always going to be the opposite sign of what you see in front of it. So in vertex form, or written like this, I see a +4. The x-coordinate of the vertex is going to have the opposite sign of what I'm seeing. So it'll be -4 instead. And then the k, the sign doesn't change. It stays the same. That's a shortcut way to remember if you want, or remember, whenever you add inside there, you can write it as subtracting a negative. We kicked off this section by seeing how to convert from convert from vertex form to standard form simply by multiplying everything out and combining like terms. However, we do not yet know how to go from standard form to vertex form. And that is the topic of the rest of what we're going to talk about today. Going from standard form to vertex form requires a process called completing the square. We will begin by talking about how to complete the square on a quadratic function of the form y equals x squared plus bx plus c. So there's no number except the 1 in front of the x squared, and we don't usually write the 1 there. If we are written in this form, then we can add and subtract this magical quantity, b over 2 quantity squared, from the first two terms, which will allow us to factor this part into this, and after combining any constants, we will be in vertex form. Now, these steps don't make a lot of sense without seeing an example, so let's do one. We are starting with x squared plus 6x minus 11. And our first question is this in the form y equals x squared plus bx plus c? And the answer to that is yes, it is, because to be in this form, we need to make sure we're not seeing anything in front of the x squared, and we're not. For this reason, then, capital B is just going to be the coefficient on the x. So I can look at this and I can recognize B as positive 6. I take the sign with it. Now, the claim is that the magical number that I need to both add and subtract from the first two terms in this original quadratic is given by b over 2 quantity squared. So I'm going to calculate what that is here. So if b is 6, that is going to mean that b over 2 quantity squared is 6 over 2 quantity squared. 6 divided by 2 is 3, and when I square that, I get 9. So we are going to both add and subtract 9 from the first two terms of the quadratic we started with, and we're going to leave the minus 11 that was there on the end. This is entirely legal because 9 minus 9 is 0, so if I actually subtracted those two things, I'd get back to the quadratic I started with. Part 2 of this says that we can take this and factor it now. Let's think about it. X squared plus 6x plus 9. If we want to factor it, we need two numbers that multiply together to give us the number on the end, but add together to give us the number on the middle. The number on the end is 9, and two numbers that multiply together to give me 9, for instance, are 9 and 1. If I add those together, I get 10, which does not match the number in the middle. Let's try again. Another two numbers that multiply together to give me positive 9 are 3 and 3. 3 plus 3 does give me the positive 6 in the middle, and that means that this factors into x plus 3 times x plus 3. Or, equivalently, you could write that as x plus 3 quantity squared. At the end of this, we have negative 9 minus 11, which equals negative 20, and all of this is now in vertex form. So, completing the square, essentially what it does is if you are not already in a form that factors into x plus a number times the exact same thing, which this guy here does not, Are there two numbers that multiply together to give us negative 11 and add together to give us 6 that are integers? The answer to that is no. So this doesn't really factor at all with our typical understanding of factoring. And in order to get to vertex form, then we need to find a way to kind of force a piece of it to look like x plus a number times x plus the same thing. And that's exactly what completing the square does. Adding and subtracting this magical quantity from the first two terms, when this is in standard form, essentially, with a 1 in front of the x squared, forces it so that we get something that factors into x plus 3 times x plus 3, or x minus 1 times x minus 1, two copies of the same binomial thing, which gets us into this piece of the standard form, or of this piece of the vertex form, and then combining our constants will give us the number on the end. Now that we're in vertex form, we would like to identify our vertex. And I'm going to remind you again that when you are in vertex form, the minus sign is built into the formula. So I can think of this as x minus negative 3, quantity squared, and then minus the 20 on the end, which is going to force the minus 3 to be our h, and the minus 20 on the end to be our k, and hence the vertex that goes with this vertex form will be hk, or negative 3 comma negative 20. So our vertex form is what we just got. And our vertex is negative 3, negative 20. Vertex form, y equals x plus 3 squared minus 20. Let's look at another example. Here we have x squared plus x plus 4. And before we can do anything else with it, we need to make sure that we are in the correct form. So the thing we're going to ask ourselves is this in the form y equals x squared plus bx plus c? And the answer is yes, it is, because again, there's no number in front of that x squared that we can see. Therefore, we can identify what b is going to be just by looking for the coefficient on the x. And we don't see any number here, but we can think of x as 1x, and therefore we can think of b, capital B, as being the coefficient on the x, which is positive 1. Now, we would like to rewrite this as x squared plus 1x, and then we're going to add and subtract some magical number right after that before we add this 4 that was on the end originally. The formula for the magical quantity we add and subtract is b over 2 quantity squared. In this case, this is going to give me 1/2 quantity squared, or 1/4. So I'm both going to add and subtract 1/4 from x squared plus 1x, and we will take it from there. Now, this is more involved than the first example, or anything we've done with factoring so far, because I need two numbers that multiply together to give me a fraction, 1/4, and add together to give me 1. So this is a little bit more challenging than what we've seen. Now, you may be able to figure that out, but if you can't, we are guaranteed that this will always factor into x plus b over 2 quantity squared. So the claim is this is going to factor into x plus b over 2 quantity squared. In our case, since capital B was 1, this will factor into x plus 1/2 quantity squared, or x plus 1/2 times x plus 1/2, and you can check that that works. You would need, if you wanted to factor this, two numbers that multiply together to give you 1/4 and add together to give you 1. 1/2 times 1/2 is the 1/4 on the end, and 1/2 plus 1/2 gives you 2 halves, or 1, the coefficient of the middle term. So you can either figure that out by looking, or you can always come back to this. Hence, this is going to become x plus 1/2 quantity squared, and then on the end, we have the minus 1/4 plus 4. I can think of 4 as 4 over 1, and then to add these two fractions together, I'll need a common denominator. The smallest number, 4 and 1, both go into evenly is 4, so that common denominator is going to have to be 4. Negative 1/4 already has 4 as the denominator. To introduce 4 as the denominator in 4 over 1, I will multiply both the top and bottom by 4. This will give me x plus 1/2 quantity squared minus 1/4 plus 16/4, and then minus 1/4 plus 16/4 is minus 1 plus 16, or positive 15/4. So I have x plus 1/2 quantity squared plus 15/4, and this right here is going to be our vertex form. I'm going to label it as such, and I'm going to box it off. Now, in order to identify our vertex from our vertex form, I'm going to do the same trick we have used so far. Vertex form is that a times x minus h squared plus k. And right now, I'm not quite looking like this because I do not have a minus sign after the x. I can make it so I do by rewriting x plus 1/2 as x minus negative 1/2, which is going to allow me to identify that playing the role of h is negative 1/2, and playing the role of k is 15/4. Hence, our vertex from this is going to end up being negative 1/2, comma, 15/4. So these together form our answer to this problem. Now, the above only works if we're dealing with a quadratic of the form x squared plus bx plus c. What do you do if you have a number other than 1 in front of the x squared? That is addressed with our next example. Completing the square on a quadratic function of the form y equals ax squared plus bx plus c requires first factoring out the leading coefficient a from the first two terms of the quadratic function and then following the steps above. Let's take a look at what this will look like. Notice here that this is not in the form x squared plus bx plus c due to the 2 in front of the x squared. This tip says factor the 2 out of the first two terms. So I'm going to take 2 out of 2x squared plus 4x. What do I need to multiply 2 by to get 2x squared? That would be x squared. What do I have to multiply 2 by to get 4x? That would be positive 2x. And so factoring that out of the first two terms will look like this. Now, we are going to complete the square as we normally would on x squared plus 2x. In this case, this is of the form x squared plus bx plus c. And so we can let b be the coefficient on the x, which is positive 2. Now, b over 2, quantity squared, our magical number, is 2 over 2 squared, or 1 squared, which equals 1. And completing the square tells us, take x squared plus 2x, add and subtract that magical number from that. So we are going to add 1 and subtract 1 from x squared plus 2x. This piece should factor perfectly into x plus a number times x plus another number. In this case, it should factor into x plus 1 times x plus 1, because two numbers that multiply together to give me positive 1, but add together to give me plus 2 are 1 and 1. Or if you prefer, you can use that formula I mentioned, x plus b over 2 squared in this case would be x plus, well, b over 2 here is going to end up being 2 over 2 or 1. So this will also give me x plus 1 squared, which is x plus 1 times x plus 1. Hence, this becomes x plus 1 quantity squared, and that's going to be followed by the minus 1 because we factored this quadratic, that is the first 3 terms, and we still have the minus 1 on the end. What do we do with that? Well, we are going to replace this piece with it. So here, I'm going to have 2 times what we just got, which is x plus 1 squared minus 1. And then I still have the minus 11 on the end. To finish getting this in vertex form, we will distribute this 2 to both terms inside the set of parentheses. 2 times x plus 1 squared is exactly what I just said. Where 2 times minus 1 is minus 2. This minus 11 is outside the parentheses, so the 2 doesn't affect it, but it still needs to come along for the ride. Our final step then is to combine the minus 2 and minus 11 to get minus 13, and hence we're going to get 2 times x plus 1 quantity squared minus 13 as our vertex form. So we have the extra step here when we have a number in front of the x squared of factoring out from the first 2 terms and then completing the square on what remains once we factored that out, and follow these steps through to the end to get our vertex form. This is the same as y equals 2 times x minus negative 1 squared minus 13. And so our h is negative 1, our k is negative 13, and our vertex thus is going to be negative 1 comma negative 13. We're going to do this one more time as one extra illustration. We have f of x equals 3x squared minus 5x plus 1, and we would like to complete the square on this. There is a 3 out front of the x squared, so I'm going to start by factoring that 3 out of the first 2 terms. This will give me 3 times. What do I need to multiply 3 by to get 3x squared? That would be x squared. And then what do I have to multiply 3 by to get negative 5x? Well, 3 doesn't give me 5 easily. I, in fact, need to use a fraction in order to make this work. In order to make this work, 3 times minus 5/3 x, when you multiply together, the 3's will cancel, leaving you with the minus 5. And so that's what I would have to do to factor the 3 out of here. Alternatively, when you take the 3 out, what gets left behind can be thought of as dividing each of these terms by 3. So 3x squared divided by 3 gives me the x squared, and minus 5x divided by 3 gives me the minus 5/3 x. It's an alternative way you can think of factoring out a number. All right, once we're in this form, we can complete the square on what's in the parentheses. So we're going to complete the square on x squared minus 5/3 x. This is now in the form x squared plus bx plus c. And in this case, our b is negative 5/3. Remember, we take the sign in front of the coefficient on the x. Hence, b over 2 quantity squared is going to become negative 5/3 divided by 2 quantities squared. And we have to do some work with fractions in order to do this out. When we divide by, we can think of 2 as 2 over 1, since it's a whole number. And dividing by a fraction is the same as multiplying by its reciprocal. So negative 5/3 divided by 2 over 1 is the same as negative 5/3 times a half, or negative 5/6 when you do that out. When we square negative 5/6, the result is going to be negative 5 times negative 5 gives me positive 25. 6 times 6 gives me 36. So this is going to give me 25 over 36. This is the magical number that I need to both add and subtract from x squared minus 5/3 x in order to guarantee that the first 3 parts factor into what we call a perfect square. Hence, this is called completing the square. So we're going to add and subtract 25 over 36 from this, and we're going to take a look at what all of this might factor into. Now, we need 2 numbers, 2 fractions in this case, that multiply together to give us 25 over 36, but add together to give us the negative 5/3 in the middle. That might be a little bit challenging for us to think about. So perhaps we want to refer back to this formula, the guarantee that this is always going to factor into x plus b over 2 quantities squared. Now, b over 2 is what was inside this set of parentheses, or negative 5/3 over 2, which ended up being negative 5/6. So I could think of this as x plus negative 5/6 squared. And let's check that this makes sense. This means x minus 5/6 times x minus 5/6. If this were to work, the 2 numbers here, negative 5/6 times negative 5/6, should multiply together to give me 25 over 36, which they do. And what happens if I add them together? Well, negative 5/6 minus 5/6 is negative 10/6. And in lowest terms, dividing the top and bottom by 2, that does give me negative 5/3. So this factors into x minus 5/6 quantity squared, and then what wasn't part of that factorization is minus 25 over 36 on the end. Okay, all of this is kind of like one giant side note, and we are going to bring it back and use it to replace the part kind of underlined in blue. This becomes 3 times what we just got, so 3 times this thing, which was x minus 5 over 6 quantity squared minus 25 over 36. And then outside that set of parentheses, we still have the plus 1. We will distribute this 3 to both terms inside the set of parentheses. This will give me 3 times x minus 5/6 squared, and then 3 times negative 25 over 36, which is minus 75 over 36. And then we have the plus 1 on the end, which is not affected by the 3 because it's not inside this set of parentheses. In order to finish this off, we need to combine the like terms on the end. If you want to, you can put 75 over 36 in lowest terms first, but I'm just going to leave it alone. And I'm going to remember that I can think of plus 1 as 1 over 1. The common denominator between negative 75 over 36 and 1 over 1 will be 36, since that's the smallest number that 1 and 36 both go into evenly. I will multiply the top and bottom of 1 over 1 by 36 in order to make that happen. And then I'll have minus 75 over 36 plus 36 over 36. Combining those, negative 75 over 36 plus 36 over 36, we will deal with the numerators first. That is going to give me negative 75 plus 36, or 36 minus 75 if you prefer to do it in the opposite order, which is negative 39 over that common denominator of 36. 39 and 36 are both divisible by 3. If I divide 39 by 3, I get 13. If I divide 36 by 3, I get 12. And so in lowest terms, we're going to have 3 times x minus 5/6 quantity squared minus 13 over 12. And at long last, we have reached our vertex form. Now, this is one of the more complicated examples of completing the square because there's so many fractions involved, just to show you that this can be done. You won't always encounter ones that look like this, but it's nice to know how to do. Now, as far as identifying our vertex goes, well, remember, vertex form is y, or f of x, equals a times x minus h squared plus k. And in our case, if you look at this carefully, what's after the minus sign here is 5/6, and that has to be our h, whereas the number on the end, negative 13/2, is going to have to be our k. This forces our vertex to be the following. HK, in this case, our h was 5/6, our k was negative 13/12. This is going to be 5/6, comma, negative 13/12. Completing the square is a lot to take in, but once you get comfortable with the process, it's not so bad to do. If you need to, you can always Google completing the square, and you can get a ton of other examples in addition to the ones that you see here. If you have any questions, be sure to reach out to me.